Let's do some work. Let's start with this picture. I don't know what's going on with this document camera. I've fiddled with all of the focus controls that are available, and it remains this blurry. It reminds me of myself on a Saturday morning. But this is actually one of the most important pictures in computer science. I don't know if you can quite see. Along the x-axis is time. So at the far left we have 1970, and then we go up in half decades to 2010 on the right hand side. So we've got a linear scale of time from 1970 to 2010 on the x-axis. On the y-axis we have a logarithmic scale. We read sort of goes up from 0, 1, 10, 100, 1,000, 10,000, and so on. And what we have here are two curves that have been drawn. So you can see, if you get, I mean, they're pretty much, they're roughly straight lines, but remember, because the y-axis is logarithmic, if you see a straight line, that means something's growing exponentially. And you can see that the captions have been carefully removed. So the top one is something or other. The bottom one, you can see the bottom one gets as far as about 2,000, and then growing exponentially, and then levels off. Whereas the top one keeps on going. So we're offered some options as to what these might possibly be about. We are offered quantities in units, and we're asked to label the two missing, to fill in the two missing labels, choosing from these four options. So A is power consumption in kilowatts. B is clock speed in megahertz. C is price in cents. And D is number of transistors. And you can hopefully just about read that these are referring to Intel processors. Okay. So what do we think the upper curve is? Is it power consumption in kilowatts? Well, if it was power consumption in kilowatts, given that the curve is now well over 1 million at the top, we would be saying that an Intel CPU processor consumes a gigawatt of power. So that's to say, to power one processor, you would need like some serious hydroelectric dam or something. So better not be that. How about price in cents? Do we believe that? Are we at the 1 million cents for a processor, $10,000? No, in fact, the curve for processor price is if anything in the other direction. This stuff keeps getting cheaper as technology improves. Actually, this pretty much goes, well, we'll see. How about clock speed in megahertz? Right? Is it the case that clock speed has kept on increasing exponentially? Well, no it ain't. And it's certainly not the case that we now have processors that run at, that are clocked in the terahertz, right? We're not going at 1,000,000 megahertz. And that's the key thing that happened. So do you think it might possibly be number of transistors in a processor? So what we're basically saying is that we're now in well into, actually it should be almost thousands of transistors. We're well into billions of transistors in a processor. And since the invention of the silicon chip, we've been basically able to double the number of transistors in a processor every year or two. So yeah, and that's continuing. There is a physical limit which we will hit maybe in a few decades' time, but we are not there yet. We are still able to make chips with more and more transistors on them. And what does that mean in terms of real life? So this is D. In real life, that means we can put more and more logic on a chip. We can put more, each bit of memory is made from a fixed number of transistors. If we're doubling the number of transistors we can put on a chip, we're doubling the amount of memory we can put on a chip. Each component that does arithmetic, again, same, fixed number of transistors required to make that stuff. If we're doubling the number of transistors, we can have more. If you have enough transistors to make one processor core, and then in 2 years' time you can have twice as many transistors, you can have 2 processor cores instead of 1 on the same chip. And that means you can do 2 things at once. So that's the way things are going. What about the other curve? You can see that it grows exponentially until about 2000, and then it pretty much levels off. What do we think that is?
Clock speed?
That is clock speed. I mean, clock speed has been growing very slightly, right about then, so it's basically saying things made it to about a little over a gigahertz, and they were a little over a gigahertz around about 2000. The machine I'm using these days, it's about 2.5 gigahertz, and that's, in the best part of 20 years, rather than just going up and up and up. There's clock speed has leveled off, and we ought to think about why. I mean, what stops you increasing the clock speed of a computer? Yeah? That's one of the things. I mean, there's one crucial limiting factor, yeah? That's another one. There's one crucial limiting factor, which is the latency of the circuits, right? One clock tick has to be long enough for signals to get through whatever network of ordinary combinational circuits you can do, right? Essentially, you know that we build these circuits out of flip-flops packed up in control circuitry. And a clock cycle has to be long enough for the control circuitry to tell the flip-flops what to do. That control circuitry has to do its computation within one clock cycle for the flip-flops to update correctly. So it's important that those circuits don't have too high a latency. That's to say that data doesn't have to travel through too many components, because these things take a tiny amount of time and that builds up. But latency is not the problem. We've got the actual circuits that we use are much faster than our current clock speeds, and we can do all sorts of tricks using the fact that we can have more transistors to reduce the latency of the components we're doing. So indeed, although latency is a bound on how fast we can make the clock, it's not the problem. You're quite right to say that power and heat are the two problems. So think about, if you want to power, if you want to do twice as much computation in the same amount of time, you have to put twice as much power in to drive the thing. So if you're worried about battery life, you know, overclocking the machine is going to cause your battery to drain faster. Or if you're not worried about battery life because you're connected to mains electricity, then maybe you should at least worry about the cost of the electricity and, you know, maybe the future of the planet, you know, global warming, that sort of stuff. But also, there's this little tiny problem with, you know, if you put a load of power in, what happens to it? It's got to go somewhere. What does it turn into? Heat. And then your problem is, how do you get that heat out of there? So exactly, you know, I touched my processor and I caught fire, right? You know, I mean, that's good. You know, I mean, it's winter, so curl up with a laptop and go to a website that uses loads of flash. And, you know, these things get hot, and the big problem is just getting the heat out of there. So that means so this is clock speed. So this means that we are faced with a new puzzle to solve as computer scientists, right? Before 2000, everything got faster and faster and bigger, and if you wanted your program to be twice as good a year later, it just happened automatically, right? You just waited a year and it went twice as fast. And you had twice as much memory and you could do twice as much stuff. It was wonderful. You know, things that people figured out in the 1970s just kept getting better and better without us really trying. Whereas since the turn of the century, we've been in a nasty spot. Namely, that although we can build multi-core processors which can do lots of things at the same time, we can't have single-threaded processes that work in sequence that do more stuff in the same amount of time. So we're busy teaching you to program in a programming language that has semicolons all over the place. And what that means is that it is not at all obvious how to split those tasks up into things which can be done simultaneously on different cores. Because your program structure says, first do this, and then maybe using the results of that, do something else. And you have no choice but to wait for the first thing to finish before you start the second thing. And in the context of what's happened to processors, this is a disaster. We are teaching you to program with a technology which was great last century, but something's got to give if you're going to be able to survive in programming this century. So now, it's first year, we've got to teach you the sequential story before you can even begin to think about what might be better in terms of being able to do multiple stuff simultaneously. But all I'm saying is, you're learning Java now That's the beginning of the story, but it's definitely not the end of the story, because this picture tells you that the execution model of Java is in deep trouble. So something's got to give. Fortunately, in later years, we'll teach you how to do something about this. But this is why it's become really interesting to be a computer scientist in the last 15 years or so, because it's suddenly got difficult again. We've got to be a bit creative, and that's fun. Yeah, so how to exploit the fact that we can do loads of things at once, but it's a disaster to do things in sequence. Major problem. Okay, so that's the sermon. Let's do something. Let's learn some other stuff. I've got another typical topic 8 puzzle for you. Let's see if we can get through it. Right. Jeepers, that really isn't focusing at all. I shall read it out to you. So it says, the thing is called a carefully assembled puzzle. And it says, I have the following software in the given languages. A basic interpreter in 6502 assembly language. A 6502 assembler in 6502 machine code. A 6502 emulator in C. A compiler from C to x86 assembly language in x86 machine code, and blah, blah, blah. There are a bunch of words here, like interpreter and assembler and emulator and compiler, and I need to make sure that you know what they mean. It's also clear that I better write with thick pens to have a chance of being able to read it on this badly focused situation. What was about that? That's excellent timing. I'm sure it's unavoidable. Okay. So, suppose we have some program P. Let's zoom out. Suppose P is a program. What should we know? What questions should we ask about any program at all? A bit like animals, really. What does it eat? Yeah? What input does the program expect? And the other question we should ask about a program is, what does it do? For instance, it might run a game for us, or it might produce some output. We need to know what the program is going to do when it gets its input. These are things to know about any given program. Okay. Right. Crucially, we can have versions of P in different languages. Right? It is possible for the same program to exist in different versions, where just like you can translate text between different human languages, you can translate different programs between different computer languages. The answers to questions 1 and 2 will remain the same, no matter what language the program is in. If those answers change, it's a different program, does different stuff. But you can still translate P from one language to another, and it stays fundamentally the same thing. The other important question in practice about a program is, do we have P in some L we can run? Right. When can you run a program? To run a program, you must have a version of it in some language that your equipment will understand. So, not all versions of the same program are equally useful. If you've got a version of a program in a language and you've got no equipment for running that language, it's junk. Okay? So, we need to start thinking about how this stuff works. We're trying to run programs on machines. Suppose we've got a machine that will run some language L. Can we run program P? Well, we can if we have a version of P in L. Then it will run on the machine. And then we can feed in P's input. And what will happen is P's action. So that's the typical picture. In order to run a program, you need to have a version of the program which you can run on some machine. You need to have the right input for the program, and under those conditions, you can run the program and good stuff will happen. Okay. So we're going to need to think about the relationship between machines and languages. Okay? M is a machine, let's say. Like my Mac is a machine, your phone is a machine, and all of these sorts of things. And inside it, crucially, there's a question of what processor it has. Right? So, there is a language, and machine code. And that's the only language M runs. Right? You ain't got a program in M's machine code, you can't run it on machine M. Yeah? You've seen machine code for Tiny. It's those bit patterns that we write as hexadecimal digits. You actually have to get the program into that form to make the machine run it. It has to be in machine code, loaded in the machine's memory for you to press go and have the thing actually do something. Okay? There's another language, which is M assembly language. Right. So that's like our textual version of Tiny programs that say things like, LDA temp and jump to more. That's text. That's not yet kind of bits in a machine's memory. And you've learned how to translate one to the other. If you have a program in assembly language, it will not run on the machine unless you have a way to translate it from assembly language into machine code. And you've learned to do that. There's this kind of program that does that. It's called an assembler. And if you have a program in assembly language, if you want to run it, you need an assembler. An assembler is a kind of program, so your assembler better already be in a language you can run, otherwise you're in trouble. If you can't run the assembler, you can't translate your program from assembly language to machine code. Bad news. So having an assembly you can actually run tends to be important. Okay, so let's talk about ways to translate programs. The key notion is the notion of a compiler. From L1 to L2. So this is a program. We have to ask the two key questions. What does it eat? It eats some program P in L1. What does it do? It outputs a new version of P in L2. So you feed in a program in one language, and out comes the same program in the other language. So that might well be useful, provided you can run the compiler. It's a program like any other. In order to use the compiler to translate a program, you have to be able to run the compiler in the first place. So hey, this is fun stuff. Not only are programs things we run, they are also the inputs and outputs of other programs. So you can see here, a compiler treats our program as its input data. So there we are. It's an important lesson to get your head around, but it's sort of inherent in the von Neumann architecture anyway, is that programs are themselves data. We can run them, but we can also process them in other ways, such as translating them from one language to another. How do you run a program using a compiler? It's a two-stage process. We've got a machine that runs L somehow, some language, and we've got an L1 to L2 compiler in L. That means, because the compiler is in language L and the machine will run L, that means we can run the compiler. So we feed in P in L1. And out comes P in L2. That's half the battle won. We have better hope that our machine also runs L2. If our machine runs L2, now we can take this thing and put it here. And we can feed in P's input, and what will happen is P's action. So you can see two stages. First, translate the program to a language you can run, then run it. Okay? So, any questions on this? So, an assembler is a special case of a compiler, where the input language is assembly language and the output language is machine code. So that assemblers are special cases of compilers. assembler compiles, and M assembler compiles M assembly to M machine code. Okay? But what about, well, that's not the only way to run a program. There's another way to run a program, which is to have an interpreter. For L. What does it eat? Two things. A program P in L and two P's input. What does it do? Whatever P does on its input. Yep.
Maybe the question if I remember rightly from skill, doesn't a compiler compile the whole code and then the interpreter does it line by line?
It's not necessarily line by line, but yeah, we just had this picture here of what a compiler, of how to use a compiler. You compile the whole program, and then you run it. Whereas an interpreter will take the program as part of its input, and it will figure out what to do a step at a time with reference to the program that's come in. So it's like the programs are the instructions, and it's always looking at its instructions to figure out what to do next. It might internally translate that program from text into some other form, but still it's not translating the program all at once. It's treating the program as a reference for how to do the computation. Okay? What is an emulator? It's an interpreter for machine code. So, for example, how do I make sure that I don't screw up when I set tiny problems? I write a program in tiny assembly language, and I have an assembler for tiny that will translate it from tiny assembly language to tiny machine code. And that assembler is written in a programming language called Haskell. And fortunately, I have an interpreter for Haskell that is in x86 machine code, and my Mac has an x86 processor, so I can run the Haskell interpreter, and the Haskell interpreter can run my tiny assembler, and that way I can translate tiny assembly language to tiny machine code. Then, how do I run the tiny machine code? Well, I also have a tiny emulator, also written in Haskell. So my Mac runs the Haskell interpreter, and the Haskell interpreter runs the tiny emulator, and the tiny emulator runs the tiny machine code. So there's layers upon layers of these things. What we do when we have an interpreter, what that basically means is we can pretend the box is able to use language L, if we can run the interpreter, we can pretend our machine will run language L just as well as its own machine code. And indeed, this was really useful. It's about, just over a decade ago, Macs used a completely different processor. They used IBM PowerPC chips. And over the course of the late noughties, Apple decided they were going to switch from using PowerPC to using Intel. And when they did that, gobsmackingly, everything still worked, because they shipped their new Intel Macs with an emulator for the old processor. So all the old stuff still ran. So machines use interpreters, and in particular emulators, to pretend to be other machines so that more programs can run. So I need to shut up fairly soon, but that's the basic stuff. Let's just have a quick look at the back end of this question. The last piece of software I have is an optimizing compiler from Java to x86 assembly language in Java. Right, so an optimizing compiler is a compiler that specializes in producing code that runs really fast. So they're good things. If you're going to run a program over and over again, but you're only going to compile it once, it's worth using a compiler that will spend a bit more time and figure out how to translate into really fast code. But the trouble with this compiler is that it goes from Java to x86 language, but it's in Java. What use is a Java compiler written in Java? Well, if you can't already run Java programs, how would you run the compiler? You need some other version of Java in order to run this compiler. But are we stuck with running our slightly less good version of Java? No, we're not. Because the very first program we should choose to compile with this compiler is this compiler. If we could run this compiler at all, we can feed this compiler into itself as its own input, and out will come a useful version of this compiler in x86 assembly language that we can run through an x86 assembler. And now we've got the good compiler and machine code. And this is actually how it's done. People who build programming languages very often write the compiler for the language in itself. And the first program they compile with their compiler is the new version of the compiler. I mean, if you like the programming language you've designed, why would you want to use something different? So that's how these things go. It's important to understand that because compilers are programs just like anything else, you can feed them into other compilers, and indeed, you can feed them into themselves. And this is not weird, this is completely standard practice. You know, the Glasgow Haskell compiler is written in Haskell. The Haskell interpreter that I use to run Tiny is written in Haskell. In order to run the interpreter, I have to compile it with the compiler. Many, many years ago, like in the 1980s, somebody wrote a Haskell compiler in a language that wasn't Haskell. But since then, Haskell compilers have always been written in Haskell. And that's the way it goes. You know, there has to have been one in the past sometime that let you get started. But once you're started, you can be self-supporting. So That's the crucial lesson, about how we use compilers and interpreters to let us run programs that are in different languages. Yeah?
Does that mean the first ever compiler of the language has to not be in that language, all subsequent ones can?
Yes, so way back, people were hard coding these things in machine code. Right, back in the day where you basically flipped switches to set the bits of the memory. So we've kind of crawled out of the slime, building better and better language technology. So now we're not starting from raw machine code anymore, but back in the day, we had to. So it's an evolutionary process. Okay, so you have a homework which involves puzzles of figuring out how to run different sorts of programs. Have a great weekend. 1 minute papers in the box, please.